So today we're going to talk about finding limits algebraically. Now, if we remember from last time, we were able to find limits algebraically through direct substitution. But there are a couple cases where we cannot use direct substitution. And of course, these are the parts that are actually more interesting. And these are the type of problems that you're going to be asked more often in a calculus class. Because if it's continuous, it's just like evaluating a function. There really is no difference between the value of the function and the limit. And it's really when those two values are different that things are much more interesting. So just as a recap, if I have a function like this, the first thing that I typically want to do, it's a rational function. I know it's continuous on its domain. So what I should do is I should try to do substitution. And the idea is if I get a real number out of it, if the function is defined, I know that that's going to be the limit. So that's going to be very helpful. So again, we know that this is the limit as x approaches 0. So we're simply going to plug in 0 for x. And when we do so, we get negative 25 over negative 5. Negative divided by a negative is a positive. And we're going to get 5 as our answer. And that is the value of the limit. But let's say we made a slight modification here. And instead of taking the limit of this function as x approaches 0, what if we took the limit as x approaches 5 instead? Well, it's still probably a good idea to try to do substitution here. Try to plug in 5, because the reality is, even if it looks like it's not a substitution problem, if you get a real number like we did in the last case, because it was the same function, it will indeed be the value of the limit. But in this particular case, we get something interesting. 5 squared is 25, and 25 minus 25 is 0. And then 5 minus 5 is also 0. So we get something that looks like 0 over 0. Now, you might mistakenly think, oh, the limit is undefined at this particular point, which actually is not true. The limit happens to be defined in a case like this. But this is something that's known as an indeterminate form. And what that means is that in most cases, the limit will exist. It's not going to be undefined. So this is not an equal sign, but we have to do more work. Okay, we have to do some more work. And one of the things that we can do that we're not allowed to do when we're evaluating functions is we can try something that is known as factoring and canceling. So I have an x squared minus 25 here. And if I try to factor it, this is going to end up being x minus 5 times x plus 5. And then the denominator, of course, is x minus 5. You'll notice that we can cancel these two factors out. And again, this is not going to be the same as x plus 5, but because we're only concerned about what happens around x plus 5, or around x equals 5, that is, this will actually be the same as the limit as x approaches x plus 5. And then if we plug in 5, we're going to get 10. So it turns out that the limit is 10. So let's just do a quick recap of what we did here. We had a limit here. We tried to do substitution. We got this 0 over 0 form, which is known as an indeterminate form. That's not an indication that the limit is undefined, but it indicates to us that we need to do additional work in order to figure out what the answer is. So what is that additional work? Well, in this particular case, we're going to try to factor, and it turns out that we can factor this. We're going to cancel factors so that if we plug in 5, we're no longer dividing by 0. And then if we plug in 5 and we do substitution now, we get a value. And this 10 happens to be the answer to the limit of the original problem here. So just to recap and generalize, anytime we have an indeterminate form, that's a good indication. It's not always 100%, but it's a good indication that the limit does exist. That is to say, it's not undefined. And an indeterminate form we saw was something that looks like 0 over 0. But there are actually a big list of indeterminate forms. So the idea is that if you try direct substitution, so if you try to do direct substitution, and you get one of these forms here, 0 over 0, and so on, that's an indication that the limit exists and it's not undefined. Keep in mind here that these are not the answers, okay? These are not the answers. You know, notice we're dividing by 0. We have infinity. Infinity is not a number. This is just the form of the answer that we get when we try to evaluate by direct substitution. And what this tells us is not that this is the answer, but this is just an indicator that substitution is not sufficient and that we need to do more work. Okay? We need to do more work. Okay, so let's do maybe a couple more examples of this so that we can see the process when the problems are a slightly different form. So this first example is going to be an example where we have a trig function here. So again, the first step is always to try to do this by direct substitution. And anytime you're dealing with a trig function in a calculus class, you should always assume that we're dealing with things in radian mode, unless otherwise stated. So if we try to evaluate the tangent of pi over 2, or we try to look at what that's going to be, what is the tangent of pi over 2? Well, if we go and we consider our unit circle, remember that the tangent is basically going to be the y value over the x value on the unit circle. So at pi over 2, which is this value up here, that's going to be, the point on the unit circle is going to be 0, 1. So really, this is going to be some kind of 1 over 0 at that point. Okay, so 1 over 0. Division by 0 tends to be something that tends to infinity, and we'll talk about this actually in the next video when we talk about determinate forms, when you actually get something that is infinite. And secant is going to be the inverse of the cosine, so that's going to be 1 over the x value on the unit circle. So that's also 1 over 0. So this is going to be the form infinity over infinity. Again, that is an indeterminate form. That lets us know that this is a problem that we cannot find the limit by direct substitution. There is a high likelihood that this limit exists, but we don't know what that value is yet. One way to think about indeterminate forms is we can think of them as kind of like a little bit of a tug of war. We've got a fraction here, and we have the numerator getting larger and larger and larger, and we've got the denominator getting larger and larger and larger. If we just had a numerator going to infinity, that would suggest that the whole thing is going to infinity. And if we had, some sort of constant and a denominator going to infinity, that would indicate that the whole thing is going to 0. So the top is pushing this function to go to infinity, and the bottom is pushing this thing to go to 0. And they're kind of diametrically opposed to one another. And really, it's more of a question of which of these two are dominating one another. Keep in mind that infinity over infinity is not necessarily going to be equal to 1 here. Again, these aren't real numbers. You can't do real math with this, okay? It's just an indicator that we need to do more work. And again, typically that work is going to be factoring and canceling. We'll see in future videos that we have other tools to be able to deal with more general indeterminate forms. But at this stage in a calculus class, the only tool you're going to typically have is going to be some kind of algebraic work, like factoring and canceling. In this particular example, we're going to try to use some trig identities. We know that the tangent of x is going to be the sine of x over the cosine of x, and we know that the secant of x is 1 over the cosine of x. Anytime we have two fractions like this, one over the other, one thing that we can do is we can invert and multiply. So if we keep the fraction that's in the numerator here and leave it alone, and then we take the reciprocal of the denominator and we cancel some stuff out, we're left with sine. So we're just finding the limit as x approaches pi over 2 of sine of x, which sine of x is just the y value on the unit circle. So that's going to be just equal to 1. So in this case, it is equal to 1, but it's not always going to be equal to 1. It really can be any value. It can be infinite, it can be 0, it can be any possible value when you have an indeterminate form. That's why it's called an indeterminate form, because by itself, we don't know what the limit is going to be. That limit is indeterminate until we do some more work. In this next example here, we're going to deal with this. Again, just like before, I want to try to evaluate by substitution. It's very tempting to want to go into some kind of algebraic mode right away, but keep in mind that if you do not get an indeterminate form and you get a real number out, that's likely going to be your answer. So we're just going to try to plug in 1. And as you can see, we've got 1 over 0 and we've got 2 over 0. Again, division by 0, and we'll talk about this in the next video, is of the form infinity. So this is going to be of the form infinity minus infinity, and that is, again, an indeterminate form. So that's not going to work. So instead, what we need to do is we need to try to algebraically manipulate this thing. Usually that involves factoring and canceling, which is something that we can do in a problem like this, but we can't do that right away. And really, in order to cancel, we need to write this as a single fraction. So we have to go back into our algebraic toolbox here, and we need to try to find a common denominator so that we can write this as a single fraction. You'll notice that this denominator, x squared minus 1, can be written as x minus 1 times x plus 1. From here, we know that we can create a common denominator by multiplying this fraction over here by x plus 1 in the numerator and x plus 1 in the denominator. So once we do that, our numerator becomes x plus 1 over, and we're going to just leave the denominator factored because we're anticipating something's going to cancel out. And then we're going to do minus 2. And again, we actually already factored that denominator. We're going to, again, leave it factored. Again, we anticipate something canceling here. Now from here, remember when you add fractions and you have a common denominator, you just add the numerators and you keep the same denominators. So we're going to take x plus 1 minus 2. So our new fraction is going to be just x minus 1, because 1 minus 2 is negative 1. And then this is going to be x minus 1 times x plus 1. And as you can see now, we can clearly see that something's going to cancel. So this leaves us with the limit as x approaches 1 of 1 over x plus 1. And now that we've actually canceled, we can try substitution again, and we actually get 1/2. So that is the real value of the limit. Again, when you're doing a problem like this, your answer is not going to be infinity minus infinity. It's going to be this 1/2 that you get after doing that additional work. So again, this is how we handle indeterminate forms, at least in this stage in calculus. Later on, you will learn L'Hopital's rule, which is a bit more powerful and a more useful tool for finding stuff. But if you haven't gotten to that point in calculus, your teacher or professor is going to expect you to be able to do it this way. Again, I hope that you found this video helpful, and as always, take care.